Okay, Bismillahirrahmanirrahim. This is a first class after the meet. Okay, so before starting the class, if you have any sort of question or comments on the syllabus or the content of our previous section, which is actually the discrete time Fourier transform, known as Fourier transform. So we have started this. So today we'll give more example on the Fourier transform. If you have any question or comments on the Fourier transform, up to the syllabus we have covered. Of course, we'll talk more on the Fourier transform today, inshallah. Okay. If you don't have any question, then we can start. As you have already seen that we have shown some simple example from the time domain to the Fourier domain conversion with frequency domain spectrum, how to draw the spectrum as well as the phase of that conversion. For example, we have given this one half to the power n un is a general example where we have found the expression as the magnitude and the phase. We have found the magnitude is this, as well as we have found the phase is like this. From these two equations, you can draw the magnitude spectrum and the phase spectrum, and we have done it. And from there, from the magnitude spectrum, which is very important for us, we can understand the pattern of the filter from the power spectrum of the system. As well, in future, we'll find that, okay, this phase parameters or the phase plot is also very necessary to understand, to design a filter. When you have reconstructed the signal back, then of course you need to combine those signals in such a way so that the phase distortion will not occur. What is phase distortion? Okay, we'll talk about this. What is a group delay? What is phase delay? We'll talk about all of those in future as well. Okay, let me ask you this question. Have you heard about this, the group delay? What is group delay? Probably in your telecommunication, you should heard about this also in your signal and system. Any of you? What is group delay? Okay. Okay, then we'll discuss about this, of course. So we have done up to this. If we have already proven that half to the power n un, if we do the Fourier transform, then we can got 1 over 1 minus half e to the power minus j omega, and we have plotted both the magnitude and the phase response. In general, when we can put it like alpha to the power n, where alpha is less than 1, we can write the equation like this, where alpha can be any value less than 1. Very important topic is convergence of x e to the power j omega. This is the Fourier transform value. It can be also written as x omega. Both are the same. Okay, e to the power j omega. Sometimes it can also written as j omega. In different way, people express this, but all are the same. That is in the frequency domain in the after Fourier transformation. Please read it. And we are in the chapter number 4. You can get it from the chapter 4 from the Krokes book. Okay, I'll not cover the detail of chapter number 4. However, you can follow each and every topic, but I will select some topics for understanding. And I should make it clear that what is our objective to to study the Fourier transform. What is our main objective? Our main objective is to understand the transformation, not only the transformation, after transforming, how we can plot it in the power spectrum, that means in the frequency domain, how it looks like, and also the phase pattern. From there, we need to understand the behavior of that sequences, that means behavior of xn. So from the xn, we'll plot x omega, both the magnitude and as well as the phase, by which we want to analyze the filter pattern. And that is our main objective. Our main objective is not to do only the Fourier transform by the mathematical tools, because it should cover in different courses, like mathematics courses. You have the mathematics course where you can do it from the time domain to the frequency domain, the Fourier transform. So I'm not give you many mathematical tasks, how to go from the time domain to frequency domain. Please do this kind of examples and so on and so forth, and it will make your life difficult from the mathematical point of view. But our main objective is to understand the process. Okay, so the process is very important. Okay, we have already mentioned that during this example, if I go back to this, whenever we have given this example, if you can recall, you can find this value must be summable. That means not must be, it should be summable, and this is a sufficient condition. Try to note this point, sufficient condition to do the Fourier transform. If the sequence like this is the sequence, if this sequence is summable, then it is sufficient that it must have the Fourier transform value. But it is not the mandatory condition. There are some other conditions as well that can make this sequence Fourier transformable. So that is why it is known that this summation, the convergence theorem, this summation makes sufficient for the Fourier transformation. And we have found that, we have shown that in the subsequent section. Yes, if alpha is less than 1, then this sequence is summable when this is from 0 to infinity. For a to the power n, it is definitely summable, and it looks like this. So we have found that, okay, this is summable. I have already mentioned it that this is sufficient condition, but this is not the mandatory condition. There are some other conditions by which we can show that, okay, this is Fourier transformable. We are starting the next example of the Fourier transform, and you will find something very related with the filter design as well in this example. We have x omega is equals to 1 for the value less than omega c or greater than minus omega c. That what does it mean? And in between, from omega c to pi, it is 0. So if I show the magnitude response, magnitude spectrum, what I have already mentioned in this topic, we can draw it, and it looks like this. Okay, so we have 1 from a minus omega c to plus omega c, and afterwards we have 0 from omega c to pi or minus omega c to minus pi. We are in which domain? We are in the frequency spectrum, magnitude spectrum. So that means we have, let's say we have a time domain sequences, and we have done the frequency domain conversion, that means the Fourier transformation, and we are now at x omega. So we start with x omega. This is the value. Now, if we do the inverse of that, which is called inverse Fourier transform, what is that? Of course, by your previous experiences, you know that what is inverse Fourier transform. You have x omega e to the power j omega n, and it is from minus pi to plus pi. Why that is minus pi to plus pi? Because that is the full spectrum, and you need to do the average of that. So 1 over twice pi, and that is your inverse Fourier transform. So I need to write it again. So we need to find xn, which is, you will find it from x omega e to the power j omega n d omega, because you need to do the integration with respect to d omega, and the spectrum you have from minus pi to plus pi, and you need to do the averaging of that. So that is the definition of the inverse Fourier transform. So this is the definition of inverse Fourier transform. If you can recall, the Fourier transform, that was xn e to the power minus j omega n, and make a summation, because xn is a discrete value, is from n is equals to from minus infinity to plus infinity. That was the Fourier transform, and this is the inverse Fourier transform. If we have done this inverse Fourier transform, so I have also mentioned here, this is the definition of inverse Fourier transform. And now, what is the value of x omega? For you don't have any value from omega c to pi and minus omega c to pi. So then we can replace this limit from minus omega c to plus omega c. And for that, the value of x omega is equals to 1. So that's why we can write it like this. So 1 into e to the power j omega is the limit is from minus omega c to omega c. And of course, it is an average. We have 1 divided by twice pi. So I believe that you are very expert on doing integration of this kind of exponential part, because this is very simple. And that is one of the reasons why we always try to make the trigonometrical equation to the exponential term. If you can convert it, then it is very easy to do the differentiation or integration. So that is the main reason why we are always interested to write like e to the power j omega n, rather cos omega n plus j sine omega n. So you can also write it like this: the cos omega n plus j sine omega n. In that case, you need to do a lot of math. So if you can convert it to simply by e to the power j omega n, that actually gives us a huge advantage by for the mathematical purposes. Okay, by doing the calculation, we have found this result, and this is true. This is true for all value. Just only n is equals to 0 is not been implemented here, because it makes 0 by 0. This is undefined. Okay, so this is the value. So we got our xn is equals to sine omega c n. Omega c means the cutoff frequency. Let's say this is the cutoff frequency, and pi n, that is the value. Now we need to plot it here, and we can plot that, of course, as you can find that if I put n equals to 0, that means x0. If you put 0, you got a 0 here. So in the denominators, you got a 0, and in sine 0 into omega c, that is also 0. 0 by 0, that is undefined. That is why, based on the L'Hopital's rule, we can find that if sine theta, if theta is very small, then it is equivalent to theta. Since n is equals to 0 or very close to 0, then of course this theta is very small. So we can follow the L'Hopital's rule. Then we can put omega c n divided by pi n, This is only for n equals to 0. Then n will cancel each other, and we got x0 is equals to omega c divided by pi. And that is this value, omega c over pi. For all other values, we need to follow this equation, the actual equation, and put the value of n 1, 2, 3, 4, and so on and so forth as well. N is equals to -1, -2, -3, and you will get a sinc function like this. And of course, this is an infinitely long sequence, both in the positive and the negative direction. So which proves that, of course, which proves that if you have this kind of sequence, you can do the Fourier transform and you can get this kind of magnitude response. So the question is, do you have the Fourier transform of this kind of sinc function? The answer is yes, we have the Fourier transform of this kind of sinc function. However, this is very important to understand. However, this sinc function is not summable. How to know that whether this is summable or not? At this moment, just believe me that, okay, this is not summable. If you want to learn more about the summability of an infinite series or any function, you need to go for the mathematical courses or mathematical terms. You can search it in the website or the YouTube and find some lecture based on the summability. Why I'm just bypassing this, because that is not the concern of our lecture. But we can just show that, okay, this is not summable. However, we have the Fourier transform of that kind of sequence as well. In the previous section, we have mentioned that if the sequence xn, and we have, let's say, n is equals to from -infinity to +infinity e to the power minus j omega n, this sequence should be summable. If that is summable, of course, we can say that we have the Fourier transform, and this is called sufficient condition, the summability. Now, what we can see, okay, this xn is not summable because the xn looks like the sinc function. But still, we found that practically we have the Fourier transform value. Now, there might be some other condition. Yes, that is the second condition. It comes. Okay, I have already discussed about this. This is not summable. We have already mentioned that this sequence is not summable. But still, we have proven that, okay, after doing this Fourier transform, definitely you can find x omega. And how the x omega looks like, we have already mentioned that this is 0, this is omega c, this is minus omega c, this is minus pi, and this is plus pi. And that actually looks like. So of course, we have the Fourier transform value, and this is the condition, the second condition. However, the sequence xn has a finite energy ex. What is that? This is the square of the sequence. Now the second condition comes here. If your sequence xn is an energy sequence, or you may say that if you have the square summability of this sequence, then we can say that it also have the Fourier transform. So that is again a sufficient condition for any sort of sequence. So number one, if that is a summable, okay, fine, you have Fourier transform. Number two, if that is a square summable, again you have the Fourier transform value. Those are one of those are sufficient condition, not mandatory, because there are some exceptions as well. Okay, so this is a very good example by which we can show that the square summability is a sufficient condition for Fourier transform value. Okay, I'm extending this example. This example actually from the Procreus book. So which example? This example we are continuing the current example. this example I'm talking about. So, okay, let me ask you one question. If I want to get this kind of a spectrum in the frequency domain, how many samples you need from the time domain? How many samples you need from the time domain? Any of you? Yes, 115.
Infinite amount.
Infinite number of sequences you need to reconstruct in the frequency domain to build this kind of magnitude response. What kind of filter is this one?
Low pass filter.
That is a low pass filter. Thank you. So if you want to build this kind of pure ideal low pass filter, of course you need infinite number of sequences. And now this is from the book. You can find it very simply. Okay, let me magnify a little bit. You'll find that very interestingly, if I got a single sample, if I got a single sample, what is the height of that sample? We have found that omega c divided by pi. That is not actually equals to 1. Okay, omega c divided by pi. If you choose only one sample, the filter looks like this, where this is omega c, let's say, and this is pi. Still, that is a low pass filter, but this is a very low quality low pass filter. If you took n is equals to 3, you'll find that the filter looks like this, little bit higher quality filter. Okay, we always target to the positive direction. That is the way how we can design the filter. So you'll find that the cutoff, the transition is very sharp. If you choose n is equals to 7, it will improve more. It will improve more. And this is the magnitude. Still, what you have, okay, if you get n is equals to 15, you can see that, okay, the scenario will improve more. If we can jump to n is equals to 70, we can find that the scenario is very much close to the value of the ideal filter. So that is the concept of the filter design. Here the number of n or number of samples are defining the order of the filter. The first value, when we have taken only one sample, is called the first order filter. 3 is the third order filter, 7 is the seventh order filter, 15 is a 15th order filter. Of course, whenever you have chosen higher order, the filter will be more like the ideal one. But what is the problem? What is the problem? If I choose n is equals to 70, as you can know that, but to find the response of a system yn, what you need to do, you need the input signal, okay, fine, and you need to do the convolution with your impulse response. This is your impulse response. Basically, this n70 70 samples, that is your system. So where n is equals to 70, it means that your hn needs 70 samples. So then you can understand that how much mathematical calculation you need to do, how many multiplications and additions you need to do there. If you choose n is equals to 3 only, it will give you a lot of advantage from the mathematical computational time consumption. So here you need to go for a trade-off, whether you want a very precise filter like this, where you have very higher order, though practically this kind of higher order is not possible, or people are not doing that. People are actually restricting them with the order like less than 20. Always try to do that, because after that the equations are making not the equations are very difficult to handle, but it takes more time. So people actually go for the lower order depending on the purpose. If you can solve it, if you can filter it out with a low order filter, definitely you should go for the low order filter. Another terms I can introduce this kind of zigzag in the corner of the transition is known as Gibbs phenomena. Gibbs, double B, probably Gibbs phenomenon. So this is another cause. We need to put some, or we need to introduce some sort of technique by which we can subtract this kind of Gibbs phenomena. What is the problem of this Gibbs phenomena? We'll talk about this more on the filter design course. However, in the DSP course, we can just tell you that if you have this Gibbs phenomena, it will also give rise of your noise signal or your signal itself in a higher magnitude, and it may even burn your device as well. What does it mean? If you have this kind of value, that means if the magnitude response having some value 1, highest magnitude, rather you have a very higher Gibbs phenomena, it likes 2 in some sense, then your voltage is like, let's say 0. Let's say your highest voltage is 5, it will be multiplied with 1, so it will be 5. But if you certainly got 2 somewhere else, that means it is also magnifying. So then 5 into 2, that will give you 10 volt. Maybe your circuit will not survive, your chip will not survive with the 10 volt value, and then it might burn. So that could be a problem due to the Gibbs phenomenon. Okay, inshallah, in the filter design course, we'll talk more about the Gibbs phenomena and how to tackle that Gibbs phenomena in practice. Okay, I always encourage that during the session, if you have any question, please raise your hand so that I can give you quick response. So category number 1, summable. Category number 2, square summable. And category number 3, they are not summable, neither summable nor square summable. For example, UN, alpha to the power n. We have already solved alpha to the power n, UN, not alpha to the power n or UN. So now we are talking about alpha to the power n or UN. Alpha to the power n is definitely infinite in the both negative and the positive direction, because n, what is the value of n? Is from minus infinity to plus infinity. E to the power j n omega 0, cos omega 0 n, sine omega 0 n. They are not neither the squares, the summable nor square summable, but those have the Fourier transform. For these type of functions, we need to introduce delta function, delta omega. What is delta omega? Of course, that is the delta function in the frequency domain. Delta function in the frequency domain. The concept is very simple. In the frequency domain, this is in the frequency domain. If you want to find the delta value, what is the definition of the delta function? As you can understand from del t, that is the same in the time domain frequency. The area of the delta function should be is equals to 1. How to find the area? Definitely, you need to integrate with a space or the time frame. So here we have delta. This is, let's say, with 0 minus and 0 plus. That means along the 0, let's say this is 0. We have minus and we have plus. We want to, this is 0 minus and this is 0 plus. You are doing the integration and over a height. And what is the height? This height is del omega. You multiplied with d omega, that means doing the integration. Whenever this space is very small, the distance between these two small is very small and conservative, more and more. Of course, the height will increase. The height will increase. And if you concise more and more, the height will be more increased. That's why this delta omega is known, probably mentioned as this, like a arrow. That means it will prolong to the infinity. So that is the definition of a delta function. That is a very hypothetical concept of the delta t or delta. Those are analog signal. They are the analog signal. The area is 1. So that is, I'm just talking about the concept of the delta function. Why I'm introducing this? Because whenever we want to solve this kind of functions, we need to introduce the delta function. Okay. The thing is, if we want to solve e to the power j omega 0 n, we can solve it. So we have this. What is this? This is your xn. You need to do Fourier transform, and let's say you got this result. So by mathematical, using the direct form of the mathematics, it is very difficult. Sometimes it's very difficult to find the Fourier transform of e to the power j omega 0 n, and it's very difficult to prove that, okay, this is the result. On the other case, what we can do, we can take it. What is this? This is your x omega, and we can do the inverse Fourier transform. Inverse Fourier transform from minus pi to pi x omega e to the power j omega n d omega, and doing the average of that. We can do the inverse discrete Fourier transform, and if we can found that the result is equals to e to the power j omega 0 n, that is enough or equivalent to show that you are getting, you are having this e to the power j omega 0 n, and you have done the Fourier transform and you have got this result. They are equivalent. So we are making some tricks. So good mathematician, they have already show that, okay, if you have this e to the power j omega 0 n, if you go for the Fourier transform, you will get this. Now as a DSP students, what we have done, we have taken this as x omega and done the inverse discrete, the Fourier transform, and try to prove that whether it is equals to e to the power j omega 0 n. If it is that, then we can say that, okay, it is absolutely correct. So we have done the same tricks here. Okay. So this is the, by definition, this is inverse discrete Fourier transform, where the input is twice pi delta omega minus omega 0 plus twice pi k, as we have shown here that. Okay. So this is the value. And we have done the inverse discrete Fourier transform of that. So integration from minus pi to pi, this is the value, e to the power j omega n d omega, and doing the average 1 divided by twice pi. This is just what I have mentioned here. Okay, now closely, if we want to see this value, of course, you can understand this is omega, which is a function of this omega 0, that is constant, a particular frequency, twice pi k, which shows that the repetition. As you can understand that in the frequency domain, if you have this spectrum, you will have that spectrum again and again. There is a repetition, and where the repetition actually been done, if that is 0 after twice pi, after minus twice pi, and so on and so forth. So that means for the baseband, you have only omega minus omega 0. This is the baseband. For the first loop, you have k is equals to 1, that is twice pi. For the second loop, you have k is equals to 2, and so on and so forth. So for this example, we put that, since we are targeting only the baseband, let's put k is equals to 0. Then from this equation, we can write it very easily. This equals to this, because this twice pi and this twice pi will again cancel each other, because twice pi is not a function of k, So you can take twice pi out of this. I can take twice pi out of this, and you can cancel twice pi each other. Then this equation can be written as this one, where this delta, since this is a delta function, you have only the delta value at the location of omega is equals to omega 0, because as delta is equals to n minus 3, where you have the value at n is equals to 3, you have the value. So delta is equals to 0. It makes n equals to 3. So similar to that one, at omega is equals to omega 0, you have the value, and the value is equals to 1 here, and here the value is e to the power j omega 0 n into d omega, and integration makes the value 1, because there is a single value, so no need to do any sort of integration. So we got the value xn is equals to this, which is enough to prove that, we have, if we want to do the Fourier transform of this, you will find what k is equals to from minus infinity plus infinity, then twice pi delta omega minus omega 0 plus twice pi k. Then that is enough. Why this is enough? Because in case of Fourier transform, this is called one-to-one function. One-to-one function means if you have a value a, if you do the Fourier transform, you will get b. It is certain that if you go back to the original signal, not the signal, if you do the inverse Fourier transform, of course you will find the a back. There is no other solution. In some function, it may happen that you will do some forward processing, you got b. When you got the reverse processing, you might have several results. One could be a, one could be c, and one could be d. That might happen. So that is called one-to-many function. So in case of Fourier transform and inverse Fourier transform, that is one-to-one function. So if e to the power j omega 0 is equals to Fourier transform this one, if you do the inverse Fourier transform, you of course find the same result back. Okay, this is how we can prove this. So this is just to prove the value. Probably I will not ask this type of question in the exam, just to show you that this is another way to find the Fourier transform value. Okay, you might think that, okay, SAR is bypassing the mathematical term. So that is why I'm just giving one example here, which is based on direct Fourier transform, where we are using un, that is the step function. I have taken this from some online sources, the solution. You can also find it in the book and online solution. Okay, first of all, we need to check the summability. So we have found that the sequence, if xn is equals to un, for minus infinity to plus infinity, this is not summable. If that is summable, how we make it, put it summable or not? Let's say xn, the value, positive values, you can make it a positive value. N is from minus infinity to plus infinity. If that is less than infinity, then it shows that this is summable. Summability, definitely, that is a concept. If it is not, then you'll find that, okay, this is not summable. So for our case, this is not summable. Now I have already mentioned that, okay, that is summability is sufficient condition, not mandatory condition. Okay, so now we try to solve it. Okay, the un, we want to solve that. So let un is equals to xn plus yn. We have divided this in two parts, where xn is equals to half for all value of n. It means that, okay, if I try to put xn, how the xn looks like, this is half, as well as half in the other side. Okay, it will move on. And the value is half. Another one, the yn, which is equals to half for n is equals to or greater than 0, and minus half is for n is less than 0, which looks like this. Of course, I have drawn this here. So this is yn, half for the positive portion and minus half for the negative portion. Now we can write it very easily that yn minus 1 is a delta function. How? By graphical representation, we have shown here. So you have yn, and this is yn minus 1. So we have shifted that. Now, if you subtract from the yn to yn minus 1, there I should put minus, okay, subtraction. So each and every part will cancel each other. Only at the 0th location, they will add half minus half, that will give you 1. And eventually it looks like a delta function at n is equals to 0. That is nothing but a delta function. So we have proven this equation. Yn minus 1 is a delta function. We know that this is the part you need to just consider at this moment. So we can also prove that 1, if you do the Fourier transform, it will give twice pi into a delta function, twice pi into a delta function. Now, in that way, we can also show that if that is a half, in that case, it will be pi multiplied with a delta function, delta omega. Since this is already, so you can do the inverse Fourier transform. You can do the inverse Fourier transform. What is the inverse Fourier transform? You can find it by 1 divided by twice pi, minus pi to plus pi, then twice pi d omega, delta omega d omega. So it's very simple to prove that the answer is equals to 1. So this is the inverse Fourier transform by which you can show that, okay, 1, if you take 1 in the time domain, the Fourier transform value is twice pi into del omega. So we can prove it. From there, the half, you can show the half is equals to, it can be done the Fourier transform, and that is a pi into d omega. Okay, I have shown the proof here, so you can go for that. Now, what about x omega? X omega is equals to this one. So we have already proven, because x omega is actually came from the half value. Okay, so x omega is equals to pi del omega. Now yn minus 1, what is the Fourier transform? Of course, that is y e to the power minus j omega into y omega. This is very simple again. If you have delta value, what is the value 1? If you have delta n minus 1, of course, that is equals to e to the power minus j omega. And then the value is the e to the power j, the 1. What is the value 1? This is 1 value is there. So this is the shifting. When you have the time shifting in the Fourier domain, it will be multiplied with e to the power j omega. So we can write this equation again. This equation is equals to this. Yn minus y minus n is a delta function. In the left side, we have done the Fourier transform of this, and the right side we have done the Fourier transform, because we already know that what is the Fourier transform of this. We have already shown in the previous lecture. So from there, okay, do the mathematical calculation, and we have found the y omega. That means the Fourier transform of the y value. We have already know that what is yn. Yn is half for n is greater than equals to 0 and minus half for n is less than 0. Sorry, n is less than 0. So now we have found the Fourier transform value. Now if we want to find the Fourier transform of un, you need to add those because this is a linear function. Yn plus xn in the time domain is equivalent to Fourier transform is y omega plus x omega, because that is a linear functionality, linear property. The Fourier transform valid for the linear property. So we have this and we are adding those two parts. After adding those two parts, we have found the Fourier transform value of this. So this is the Fourier transform value of un. And this is the direct method. As I have already mentioned that for this kind of function like alpha to the power n, un, cos omega 0 n, sine omega 0 n, you need some tricks. And this is the tricks what we have done. So first of all, the un can be divided at xn plus yn, where xn is equals to half for all the value, yn is divided in different pattern. So we have done a lot of things, and after that we can prove that. So as a student of the DSP class, we are not dealing with mathematics. We are dealing with the spectrum analysis. Okay, so that is why I'm not interested to do this kind of mathematics. However, since we have shown it, please try to recall or try to find it convenient for the exam or the Viva session, how to find the Fourier transform value of un. Okay, so up to now, do you have any question? We have done some mathematical part today, not much on understanding part, typical understanding. Okay. Okay, let me start the other section of the Fourier transform with an example. That means the upsampler. What is the objective of this section of lecture? If we do the upsampling in the time domain, let's say we have a signal, we have upsampled that signal with a value L, and we have got the output yn. Of course, yn is equals to x n divided by L. At this moment, with our experience, we know that how it looks like in the time domain. How it looks like in the time domain. If I want to draw the things, you'll find it very convenient that, okay, we have found this kind of parameters. Let's say we have this sample, this sample, this sample. Okay, if we do that, this is our xn. If you go for the upsampling, what happens? We are introducing some extra sample in between. I believe you can recall the thing. We are introducing some extra sample in between. So that is the sequence. And after that, if we pass it through a low pass filter, it might looks like this. Previously, it was like this, and now it looks like this. The frequency is increasing or decreasing after having the upsampler. Frequency, yes, 115.
It's decreasing.
It's decreasing by the factor of L. Definitely by the factor of L. If you put L is equals to 2, then frequency is decreasing 2 times. If you put L is equals to 3, then it will decrease by 3 times, and so on and so forth. Okay, so that is in the time domain. That is in the time domain. Now, if we think about what actually been happen in the frequency domain, In the time domain spectrum, we can think of, okay, the frequency is decreasing or increasing. When there are a lot of sequences combined together, definitely you need to understand what will happen in the frequency domain. So our main objective of this section is that after doing the upsampling, what will happen in the frequency domain, we need to understand it properly. Okay. Okay, so start with some definition. Okay, of course, this is the definition of upsampler. So where yn is equals to n, yn is equals to x n by l, where n is equals to 0, plus minus l, and so on and so forth. And for other value, when for other samples, it will be 0, since it will be implemented implanted inside two samples. Okay, so this is y, capital Y omega in the frequency domain. So what is your sequence? X n by L, then multiplied with e to the power minus j omega n, and n is from, not from minus infinity to plus infinity, n is for 0, plus minus L, plus minus twice L, and so on and so forth. Because for other values, it is equals to 0. You do not need to go for the Fourier transform of that sequences. What does it mean? If you have the sequences like here 0, 0, 0, and 1, 1, 1, you just need to consider only these values, because the Fourier transform of 0 sequences are zeros. So no need to go for that. So that, what does it mean by this equation? Okay, so here we have done a small tricks. Okay, let's n by L is equals to m, which gives our equation like this. Now, what is the value of n is equals to m into L, or m is equals to n divided by L. So what is the value of n? N is 0 divided by L is equals to 0. N is equals to plus minus L divided by L, that shows plus minus 1. Plus minus twice L divided by L, that plus minus 2, something like that. So what is the spectrum of m then? The spectrum of m is equals to 0, plus minus 1, plus minus 2, up to plus minus infinity. So we can say that the spectrum of m is from minus infinity to plus infinity. The spectrum of m is from minus infinity to plus infinity. N by L is replaced by m, and e to the power minus j omega, and n is equals to, of course, n is equals to ml. So we have written like this. So I believe that this equation is very simple to understand. We are replacing, just we are letting this number, and there is no harm to let this. Now, if you can think of it, the m is a dummy constant. You can write this equation as n is equals to from minus infinity plus infinity xn and e to the power minus j n L omega. And here you can find that if you consider with the actual value of xn e to the power minus j omega n, you are adding some extra L value there. You are adding extra L, which is multiplied with the value of n, which is a pattern of n. Let me show it. I have shown it here. Try to understand that this omega is a function of this omega, where this NL, n is a variable where you are putting n is equals to 0, 1, 2, 3, 4, any value. What is the value of L? Let's say L is equals to 2. So all the points, when you are taking the value e to the power minus j n omega, previously you are taking n omega, now you are taking 2n omega. So that's why e to the power minus j twice n omega. So twice n makes the exponential term different. So if we consider this equation with our original equation, the spectrum now can be written as this. Previously, if I have our xn, do the Fourier transform directly, I will find x omega. Whenever I put x n by L and do the Fourier transform, I will find x L omega. I believe that is clear. That means if we have, yes, 72, just a minute. If we have previously the spectrum was omega, now that spectrum is equivalent to L omega. So L omega is equals to omega. That's why if I want to distinguish between these two omega, I just put a star just to show that this is the new frequency, new spectrum or the frequency. Then we can write omega is equals to previous omega divided by L. Previously, if the omega is equals to, let's say, for example, if the omega is equals to pi, now the omega is converted as pi by L. So here I have written here L omega star is equals to omega. How we can find that? This is the upsample value, and if we compare the upsample value with our x omega, we can find that the y omega is equals to x L omega. If we want to make the equivalency between these two, from there we can find that the new omega L omega was equals to that, and omega star is equals to omega divided by L. Let me show it in the graphical representation, which will help us to understand. This is the spectrum of your xn. This is the spectrum of xn. Let's say this is the higher frequency. This is the higher frequency negative value, and this is the second loop. This is the baseband. This is the second one. This is the second one in the negative direction. Now, if you perform the upsampling, that means this is your y omega. If you want to perform this, and which is equals to x L omega, you'll find that all the value, all the frequency component, like if there is a omega h, it is now converted to omega h divided by 2 L. This value, that means this value, what was the frequency over there? That was twice pi. Now this twice pi value will be go back, and it actually mentioned as twice pi by L. The second peak will be at the location of twice pi by L. However, the twice pi will remain at the same location. The pi will remain at the same location. So if I clarify this pi with the spectrum of omega, they will remain at the same location, but this value and this value, all the values are squeezing to the left. And due to this shifting, you can now find that previously your highest frequency was there. The first baseband was there. Now your baseband is squeezing here. So previously, if you want to put a low pass filter like this, okay, you have put in a low pass filter. If you are putting that same low pass filter here, what will happen? You are getting some extra signal. Let me show that extra signal with some other color. You are getting some extra signal here, and which is equivalent to this part, and which is exactly to this one. So you have some extra signal which makes your life difficult, and that is why you need to think of and you need to design your low pass filter accordingly. So this is the critical part of the upsampling. If you have done the upsampling, you need to think of the second lobe, whether it is transferred inside your pi. If it is like that, you need to consider your low pass filter. You need to consider the design process of your low pass filter. Otherwise, you are in a trouble. If you want to carry through the same low pass filter here, the same low pass filter means the same kind of low pass filter here, you are getting some extra signal, which is exactly like this and which is showing here. And that makes the problem. Okay, I believe that you need to go through this part again and again to understand the process. I believe that hypothetically you understand the thing. If you have xn, if you go for xn by L, definitely the frequency will decrease, and that actually been shown here. Maybe it might be difficult to understand it from the equation point of view. Just try to go through it for several times. You will find it easy, inshallah. Yes, 72.
Sir, in the equation, am I audible?
Yes, yes.
Sir, that equation that you have given, the arrow marked 1, xn e to the power minus jn l omega, when you are converting it into the m domain,
Yeah.
shouldn't there be an ml square?
I'm not converting to m domain. If you can follow that, m is a dummy constant. Dummy constant means it's actually been any value, no problem with that. So n by L is equals to m. I have shown that. From there, I can find that m, the value is 0 plus minus 1 plus minus 2 and so on, plus minus infinity. So the limit of m is from minus infinity to plus infinity. That is the limit. So now if you just consider it with your value xn, n is equals to from minus infinity to plus infinity e to the power minus j omega n. If you consider this with this one, is it inconvenient if I choose this m as n? If I choose it like this, is there any problem?
Sir, in that case, I think I got confused because in that later portion in the arrow marked 1, you wrote e to the power minus j n l omega. If you remove the l over there, then I think it will become easier for us to understand. There shouldn't be an l over there.
You are talking this?
No, the arrow marked 1.
This one?
Yes. If
If
you put L over here, then when you convert the N to M, what happens is I write N as M into L. So ultimately it becomes ML square.
No, you are not converting again because, okay, yes, I got your point. You definitely have this right to say this because how can I tell you this? Whenever from this equation, I have written this equation. What is m? M is a dummy constant. I am telling that this is from minus infinity to plus infinity. Again, what is the limit of n? Again, the limit of m is again from minus infinity to plus infinity. If that is so, can I replace the m with n? The answer is yes. So that's why I am replacing this m with n, and also this m with the n value, and e to the power minus j m with n value.
Yes, sir, I understood now.
Yes. So of course, let this equals to this, and then we have write this equation again. When in common sense the n and m, they are actually the dummy constant, then we can change that. They are equivalent. This is only been done just to show the equivalency between x omega and what is xl omega. Otherwise, you can put it in the different format, no problem. Okay. Okay. If you have any confusion, then we can discuss it in the next class, inshallah. I believe that this is enough for today's class. Okay, thank you for your participation.